All right, good afternoon, everybody. And today we should really talk about your lecture number 5 and number 6. Let me make some announcement there, and then we'll talk about the stuff. Okay. Well, the workflow for the session will be just as usual. Some quick announcement. Yeah. So your lecture week number 7 has been released. I think this week will be a little bit heavier on the math side. Well, it's not really advanced math. It's just about manipulating the equations and also try to add up, like a geometric or arithmetic sequence. But I think the more important lesson to learn over here is about how to connect the math to the Java programming. I think that's more important. But we're going to start with some very interesting idea about circular array. So that will be some improvement for implementing the QADT. That's something you will see. We started with that. And also we're going to do the so-called amortized analysis of dynamic arrays. So this will be the most exciting part, I believe, for this week. We're definitely going to talk about, rather than having some fixed size array that simply wouldn't give you any flexibility of resizing the array whenever needed. But with a dynamic array, we will be able to do it. And we got two different strategies for using dynamic array. So one is called fixed increments, and the other one is called doubling. So these are the two common strategies, and we're going to learn about them. The code itself is actually rather easy to understand. It's not too much extension to what we have already got. But I think the main interesting idea is to really argue about their running time. And we're going to distinguish between the worst case running time versus average case or amortized running time, meaning average. So that's something you will learn about. I would say spend a very good amount of time really going over the math together with me, and then really try to do the exercise yourself as well. So maybe later on when we actually do the exam later, I will definitely expect you to do some manipulation like that, right? We'll see. Anyway, so study this carefully and post your questions on the Google Doc. And we'll go over a few more examples on the recursion. So as I gave you the background study, let me show to you, right? I just explain that. If you go to your 2011 site, and if you look at from last week, right, week number 6, you will see there is one background study section about basic recursion. So for this course, we assume you already learned about some basic recursion from EECS 2030. So I just cannot cover everything from scratch. So I think the best way for you to catch up is to really study any lecture that's necessary for you to maybe review the basics about recursion, especially how you do recursion on arrays, and also how you decide methods are recursive, things like that, the basic stuff. But for the lecture number 4 for recursion, I just started talking about the more intermediate examples. I started talking about binary search this week number 7, and I'll talk about the remaining, hopefully 2 to 3 algorithms that's kind of recursive. We want to talk about merge sort, we want to talk about quick sort, and also Tower of Hanoi if we got any time left. We'll see, right? And then we're going to move on to the tree ADT. We're definitely going to spend quite a good amount of time in the oh, can you guys still hear me? Is somehow my computer said my internet is not stable. You guys are okay, right? I want to make sure.
We missed the last 3 seconds.
Oh, okay. No worries. Okay, sure. Yeah. So the last 2 or 3 seconds, which is about, we're gonna still cover merge sort, quick sort, and also Tower of Hanoi, when time permits. Yeah. Sorry for the lagging. I mean, it doesn't really happen often. Anyway. Okay, so that's about the basic recursion you would like to catch up for yourself, and then we're gonna go over the more intermediate examples in the lecture. And also, if you when you went over part A1 for week number 6, you also suggested about some references for you to actually go over, right? So that's something I will need to rely on you on the basics. All right. Okay, and then we're gonna learn about how you can derive running time from recursive algorithm. So if you recall the lectures that we did from week number 1 and week number 2, we mainly just try to analyze algorithm with iterative implementation, like with the loops, either while loop or for loop, and maybe sometimes we got nested loop. That's kind of the stuff we did. But in order to derive the running time for recursive algorithm, which typically does not contain any loop, in that case, how are you supposed to argue about their running time? So that's something you will learn about. So I did 2 examples in very much detail this week. We're going to see the more sophisticated example next week. So you do have some time to really get yourself mentally ready for the more advanced derivation. But I'm pretty sure in your later EECS2011, the design and analysis of algorithm course, I think you'll learn about more about recurrence relation. But we just cover just enough, so you will be okay for the course. Right, so just about your assignment number 1, I still need to touch base with the TA. I did give my some the submissions to the TA for some for the grading during the reading week. So I just need to touch base with them. Hopefully, I can return to you. Maybe not this week, I don't think. So hopefully by the end of next week, I'm hoping. Right, I'll keep you posted. But everyone is definitely being actively graded. Once it is ready, I'll release the result. And you guys definitely got a chance to speak to me if you got any concern about the grading. That's okay. Alrighty, that's about the announcement I'd like to make. Do you guys have any questions? Any administrative question you would like to ask? Anyone? Okay, I'll pause for a moment in case you got any questions. You can feel free. Will there be any partial marks for the exam? Assuming that the exam is going to be in person and the date is going to be scheduled by the registrar office, that means we're going to use paper and pen. So in that case, I think I think the format for the exam will be different, right? I mean, in-person exam versus online exam. Midterm, what do you mean the midterm? Are you talking about written test or programming test? And what do you mean partial marks? I mean, we actually specify in the test guide, you're going to be graded by, the JUnit test cases. So if you pass one test case, you get a marks for the test. If you fail one test case, you don't really get a marks for that, right? So I'm not too sure about what you meant by partial marks. So there is no like a half passing a particular test case, right? For example, if we got, let's say, 20 test cases in total to run your submission, in that case, depending on how many you actually pass out of 20, right? So that'll be your mark. So maybe that's what you meant by partial marks. Right? It's definitely not either you get 0 or 100. It's definitely not like that, right? I think it really depends on how many test cases you can pass. All right, any other questions? Anyone? If no, then I'll move on to our the technical stuff. Alrighty, hearing none, seeing none, let's now go on. The only question I saw on the Google Doc for both week 5 and week 6, I presume everybody's okay. That's the best assumption I can make. Everybody is clear about what's being covered, so you're okay. But that's fine. We'll see. So, but just remind you very quickly, right? If you look at a semester calendar on the course website, right? You definitely want to make sure you keep up with the lecture, given that they're pre-recorded. They're flexible, but meanwhile, you want to make sure you stay on top. If you go to the semester calendar, we are now over here this week, right? Over here, you can see your written test number 2 is going to happen at some point. It's not exactly urgent, but I would say you definitely don't want to wait until we cover so many stuff between written test 1 and written test 2 and study that. It's up to you, but I would say don't do that. It's definitely not going to serve you well. Once you go beyond the course, you will simply forget about all the details if you only cram the information before the test. So I don't see any other question on the Google Doc. The only one I saw was this one here, just about your written test number 1. I can talk about it very briefly. I think it is rather basic, as we discussed in the lecture about the syncly linked list. Mainly, it's about these two scenarios. Scenario number 1. Let's say we are trying to actually add an element at index I with the reference to I-1th position, right? That one there, the answer is somehow syncly linked list can give you better performance than array, right? That's something we actually spoke about before. For example, let's say if this is your chain of nodes over here, right? Let's say this is, let me just draw a little bit more. Okay, like that, right? Let's say that's your syncly linked list. If this is the node, you want to add an nth position, right? Let's say removal. Addition would be something similar. If you want to remove, let's say this particular node at nth position, if I only give to you the reference to this particular node, is it going to help in the performance? Well, as we discussed in the lecture, if you do this, it's not going to help. It's still going to be bigger of n. Because in order for you to really add a node at nth position, in that case, to really remove this particular node in the nth position, you will need to set the next reference for the previous node over here. In that case, if you are given this particular reference over here, that will be the n-1th position. In that case, you will be able to use just bigger of 1 time computation to achieve it, right? I'm just highlighting this right now, so that's something we discussed in the lecture. So if you got any doubts, you should really refer back, right? Alrighty. Let me say it again. So let's say you want to remove a node at nth position over here. If you're only given the reference to exactly the node at nth position, in that case, it will still take you linear time because you definitely still need to get the node at n-1th position. In that case, you still have to go all the way from the beginning until over here. So that will take you linear time. On the other hand, if you're given the reference to the n-1th node directly, in that case, you'll be constant time. Right, so that's basically what I want to say. But for arrays, whenever you want to remove or delete, you definitely have to shift, the elements to the left by 1 position, as we discussed in the lecture. Right. Right. Any follow up to this, in case you still have doubts? But definitely for your written test number 2, you still have to know this kind of stuff because the new stuff that we cover since your written test number 1 was the doubly linked list. But doubly linked list is highly relevant to singly linked list. So you make sure you kind of understand this basic stuff, right? You want to make sure. Any follow up to this? Anybody? Anyone? Already hearing none, seeing none. So now I'll open the floor for any additional questions related to the lecture. Anybody? Any question to the lecture 5 and 6, right? All right, I'll pause a little bit longer to see if there's any question here. Anybody?
Oh, sir.
Yes.
Nobody's gonna ask a question. Sir. If nobody's gonna ask a question about lecture 5 and 6, can I ask a question about simply linked list and doubly linked list? A very quick question, like not in terms of materials, just in terms of like can I ask about that?
Okay, so what's your question? Sorry, I'm not really following. Just go ahead. I'll turn my volume up a little bit.
I didn't say my question yet. I was just saying that since doubly linked list is more flexible, we could do more things with doubly linked list, right? Oh, is it okay? Like
Yeah.
Why do we have? Sorry, can you hear me?
I can hear you. Yes, I'm listening. I'll let you finish the question first, and I'll respond. Yeah.
Okay. Why would we like? Is it okay? Like, do you recommend that we should just follow up with doubly linked list because it's always it's always better than simply linked list. Other than it might take some more memory space, but overall it's just more flexible.
I
just wanted to get your suggestions.
Absolutely. I know exactly what you're asking. Yes. I think okay, there are two parts over here, right? Let's say for you're basically asking should when you develop your code, should you use singly linked list? Singly linked node or doubly linked node. So let's say I would say for your developments, in which case you have the control over what you can use. For example, you're developing your own projects, maybe maybe when there's no requirements as to which singly linked node or doubly linked node should be used, I would say whenever you have your developments, if it's completely under your control, then in that case, I would suggest always use doubly linked node. I agree. For the reason that it supports the previous reference, which can definitely make some operation which would take linear time for the singly linked node. But for the doubly linked node, you will be able to improve it to the constant time. So I would say definitely go for that if you can control. Okay, so that's pretty clear. However, I would say the other case, it depends, right? So let's say for your maybe programming test, and possibly for your written test, or maybe for your final exam, you might be constrained about what you can use, right? I would say pretty much like for your programming interview, for many of the questions I have seen so far, usually they assume you only got access to singly linked node, but not doubly linked node. I guess maybe the rationale is the interviewer, your potential, your prospective employer, they actually want to see how we can program under such constraint without the access to the previous reference. So I would think you should really know both, of course. So I would say in this case, the singly linked node, singly linked list is more likely. Which I agree, with them, because I think when I design some algorithm for question, I think sometimes actually, if I restrict that to be singly linked node, I can see a little bit more from how you can program. So I would say it really depends on scenario. But if you really got 100% control and there is no any programming requirements, definitely choose doubly linked node. But if you actually got any constraint, you have to go with whatever that's required for you to do. Okay. Awesome. Good. That's a good question. Good. All right, guys. Any more? There's always next week. You can still catch up with the lecture and ask me next week. That's okay. But don't procrastinate for too long, right? Or you can just drop by my office hour. One more office hour tomorrow, if you want to. All right, I'll pause a little bit longer, right? And I do have one thing I would like to discuss since you guys actually decided to come, which I appreciate. So I definitely should do something together with you. So you'll be worth your time coming. I'll wait a little bit longer just to make sure everybody's okay, at least for lecture number 5 and 6. And for lecture number 7, I definitely recommend you actually try to go over with the math that I try to derive with you in the lecture video very carefully, right? That's something you may just have to do on your own. Not too sure if we can do that online, but maybe in the in-person exam, that's going to happen in April. In that case, you can make sure you can do it on the paper, right? Okay, I'll pause for one more moment. If not, then I can move on to what I really plan to do today. All right, hearing none, seeing none. Why don't we actually do some exercise together, right? I thought maybe since you guys just had your programming test number 1 about singly linked list, so why don't we go over the solution for both of them? Why don't we do that? Okay. I think I also want to give some advantage to maybe your fellow student for tomorrow. So I want to go well, I'm actually maybe you chatted with your fellow student after the test. I think for both sections, I mean the test held in both times, I only gave one method for each one of them to really program. So my intention is it's only your first programming test for this course. I wanted to make it light, so you can at least get used to the workflow, get used to the format. But we got another programming test. I would definitely expect your programming ability to be a little bit higher than now. Right, that's something I will give you some more guidance maybe a little bit later. But for now, we're okay. Why don't I go over one question with you today, and then I'll go over the other question tomorrow, and then I'll definitely make the recording, the source code available on the web. You can definitely take advantage of them. So study them both. I think they're roughly equally the same in terms of the level of difficulty, right? So why don't we do this one here? Maybe some of you actually took the test maybe on Tuesday, in which case this might be the first time you see this. Or if you took it on Monday, this is the version you had, which is about doing some circular shift, all right? Just for those of you who may be seeing this question the first time, right? Can I just, how about I just give you about 1 minute or 2? It's now 4:23. Let's wait until 4:25. Take about 1 minute or 2. At least take a look at the header, take a look at the question itself, and then we'll go over the solution together. Okay, I'll give you 2 minutes. Take a look. Take a look at the header, the description, and also some JUnit tests to see how it works. And then we'll talk about it. Okay. Okay, 1 more minute, and then we can go over some rationale of designing the solution, and then we can program in Java. I'm going to use Eclipse. Already, yeah, at least everybody is kind of familiar with what's going to be solved, so you wouldn't be so lost if I talk about it, right? So let's now talk about, I'm not going to just draw objects as detailed as what I did before. Let's try to focus more on the idea. So when I write a Java code, it wouldn't seem so strange to you, okay? If this is actually what you solved in your test, you can definitely also compare your solution with mine to see which one might be more intuitive to you. We'll see, okay? So let's say we got this particular linked list. Let's say, let me draw that, and then I'll talk about a high-level idea, at least how I thought about it, okay? So let's say we got a linked list of size 4, right? Actually, I do have a linked list over here, right? I don't want you to look at the solution just yet. I'm going to go over a solution with you. So let me just copy this diagram over here, right? Let me copy that, and over here. Let me describe my logic of how it works, and then you can feel free to speak up if you got a different logic, okay? Let's say this is our linked list of size 4, right? So we got these string values stored in the linked list, right? So the first one is I, and the second one is loved, I love. And also, let's say the third one is linked. And then list over here. And this is definitely N1, right? That's the first node. And the last node is definitely pointing to null, right? So that's an input for the linked list. And let's say now we are calling the method to say we want to return a new list. However, we don't want to create any new nodes, right? So this is kind of the opposite to what you did in the assignments. In the assignments, we actually said, actually for this one here, yeah, actually similar. Sorry, I take it back. It's in the assignments actually, you know what? Let me just, I don't want you to get confused. I think for your assignments, we said that you must create actually new nodes. That's why we got a no aliasing, right? So this is opposite. In the programming test, you are not allowed to actually create any new nodes. That's why I didn't use the no aliasing assertion. Sorry about the initial confusion, right? Anyway, but you just gotta go with whatever the requirements is imposed on you. You want to make sure you follow that. So what we're gonna do is we're going to shift starting from N1 over here, and we want to shift by 2 positions over here. So how exactly is it going to work, right? I think the main thing is we want to know, well, first of all, let me just give you some very quick visual over here. If I want to, let's say this is my list over here, right? If I shift my list by 0 position, it's going to be no change, right? If I want to shift my list to the right by 1 position, so you want to imagine that you're going to push the list to the right by 1 position, in which case the last node need to be wrap around to over here, right? That will be the case when we want to shift by 1 position. What about we want to shift by 2 positions? In that case, you have to imagine that you're going to go for you're going to shift by 2 position over here. That means you want to stop over here, and then whatever that goes after this position here must be wrap around to the beginning, right? So that means eventually it's going to look something like this. The same order is going to be preserved, and then we're going to do this. That's basically the idea. Of course, you're going to make sure you're going to set the next reference properly as well. All right. So hopefully so far so good. But now the question is, how exactly do we find out the point where we try to wrap around to the beginning? That's about the point, right? So you can see over here, in this case, this is really the point to wrap around for the shift. Over here, for this particular example, since we want to shift to the right by 2 positions. And let's look at the indices. The indices is actually 0, 1, 2, and 3. So these are the indices, right? Let's still follow the convention we did in the lecture. Indices for the linked list, like arrays, they'll start with 0. And in this case, also we got the size of the list is actually 4, right? And then we have found that this is the point where we should really start thinking about exactly how to really wrap around this part over here to here, right? That's what we need to think about. Exactly how do we get this number over here? How do we get this index? So we need some formula over here. Get node add method can help. I agree. Yeah, you can definitely. I presume maybe you implemented some helper method, or you just use helper method in the actual test. That's okay. We're gonna do that as well. Yes, I agree. But how exactly do you get to this position? That's my point. You can see here we got n is actually equal to 2, and this position over here is actually 1. Starting from position number 1. We should really do the wraparound. Given the size 4 and also n is equal to 2, how do you see the relationship over here? We got 3 key numbers over here. Index 1 over here, and also size 4, and also n is about how many shifts we actually want to do. Let me so what's the relationship between these 3 numbers? Can anybody see? Okay, let me call this number over here, the green one over here. Let's call that maybe the shift starts at over here. It's going to be somehow defined, right? Excuse me. So admin, I can definitely see you're trying to do that. Very good. So yeah, that's exactly how you should derive the number. So that'll be the size. If you say size minus the number of shifts is going to be 2, which is not exactly 1. So you may just want to try to begin with. You want to try to say size minus n and then minus 1. Exactly. So this will work for now. There might be some boundary cases you have to handle as well, but I would say we start with the general case first. That's how I program the solution myself. Alrighty, guys, any questions so far? I think it's important for you to see how this particular little formula is derived. I think that's a key point. Okay. And let's say once we have calculated this particular value over here, we know that this is the point to really try to set up the wraparound. Right? In that case, what should we do? Very quickly, what we should do is, so this part over here should no longer be pointing to this, right? So this part over here should now become the end of the resulting list. So this part over here somehow should be set to null. Let me use orange. Okay. So this part over here should somehow be set to null. And then you should really wrap around this part over here, right? To over here. But let me not do that. Let me just try to see how exactly do we set a pointer. The pointer to set is to make sure we say that, so this will become the new head, right? This is now the new head after the wraparound. And then this part over here, rather than pointing to null, is going to join this part over here. That's basically what's going to happen, right? So you just focus on the orange over here. We want to do several things over here. Since we know this is the point where the shift will actually start. So we want to make sure this part over here up to now used to be the earlier half of the list. But after the shift, it will become the later half of the list. So that's why we have to say the new head should be exactly after the point of shift, which will be the new head over here. And then the new head is actually going to join the beginning of this particular part over here, right? Hopefully this visual summary actually makes sense to you. If you have that idea understood, I think you already know how to get started. All right. I'll pause here for a moment just to see if you got any questions about this so far. That's basically what you need to understand before you can program. Of course, for now, we haven't really programmed certain boundary cases, in which case I'm going to include in my solution. You can also study them as well, just to trace the code a bit. Okay. Any question about what I said so far, about the rationale, about how to understand how the problem should be solved? Anybody? In my case, I'm just going to assume I don't have that get node at method available, so I can just program from scratch very quickly, right? Everybody's okay? It's clear? Okay. And of course, I got a solution over here, but let's now type line by line together. And then I can either leave the tracing to you, or we can do it together. We'll see. Okay, why don't we just program the solution first? Okay. All right, let's now move on to Eclipse over here. If you go to the website over here, if you, I'm pretty sure you got to start a project already for your test, but in case that's not the version of test you took, you can simply go under week number 5 and week number 6. You can see the Q&A stuff over here. Under problems over here, I gave access to both shift to write by. This is a version taken on Monday. So this is the what was taken on Tuesday. So that's the one I'm going to discuss tomorrow in the Q&A for your fellow students. So you can definitely take advantage of both. You can download the specification for the problem. You can also download the starter code to program, to practice yourself. I think that they are reasonably okay. It's not really that difficult, but I think at least it's more than easy. All right. Let's now try to program the solution together. Right. So if I go, this is also the project I'll make available to you. Let's now program this. Okay. Over here. Right. Let's now we're gonna calculate the size as well, right? Assuming that we don't have the size method over here. So integer and size equals 0. Very easy to calculate. And also to do that, we need some current. So we're gonna say node E. Remember, this class is such generic. In your starter test, we only tested you on the value for string. Of course, you want to make sure it works for integer as well. And the way to make it work is really make sure you program generically according to E, right? So that's why I'll say node E over here, and then I'll say current is equal to just the head to start with. I'm just going to go over the entire list to see how many nodes there are. That one should be very easy since we covered that already. Let me just say return null, so I don't have any compilation error, just for now. Okay. And then we're going to, also, I need a tail as well, right? We'll see how the tail can be useful. Basically, the tail can be useful in the following way. Let me just give you a look ahead over here. Once we figure out the point of starting the shift, you can see somehow we have to make sure the last nodes over here should really be connected to the first node over here, right, for the shift. So this node over here is the tail, which we have to calculate at the same time. You have two options over here. Either you can actually try to calculate the size using one single loop, and you can calculate the tail using another loop that's not nested. If you do that, it's simply just n plus n, so it will still be linear time. So it's not going to make the algorithm very inefficient. But I think I can just calculate both the size and the tail in a single loop. That's something I can do. I'm pretty sure you can do as well. All right, let's see this. So tail is simply equal to null to begin with. Right, so very standard, we say current not equal to null. In that case, I'm going to say size plus plus, right? And also tail is simply equal to current. So the idea would be, as soon as we actually, and then, of course, let me just do one more line, of course. Current is updated to current dot get next over here. So we want to make sure when the current is updated to something that's actually null. So that means we are really talking about this particular node over here, because only this node's next will be null, right? That's exactly the property we spoke about, right? So we can really calculate the size and the tail at the same time, right? Already. And then now we can do several things over here. So now we know about the size and we know about the tail. And now we should really almost ready to really start connecting. I have some special case over here. In case the size of the list over here is simply just 0, in that case we just return null. All right. If the size is equal to 0, in that case we just return null. And then that's a special case. Otherwise, you can see this is actually we got at least one node are in the input chain, right? In that case, what should we do? Well, we should really calculate this particular index, which Adnan actually correctly said what it should be, right? Sorry, let me look for my Apple Pencil. All right. There we go. So we need to figure out exactly what this index is, right? And what we should do is we should really say, let's say integer over here, let's say number of shifts over here. Well, this is actually important, right? There is also something you should really figure out as well. Let's say at the moment we actually got 4 nodes over here, so the size is actually 4. But what if the number of shifts, for example, number of shifts I want to do is actually 5? What does 5 really mean? Because remember I said in the test it's actually arbitrarily large number. How can we know exactly where to go if I want to do 5? So I can claim that shifting for 5 position is really equivalent to shifting for 1 position, right? Let's try. If I only shift for 1 position, right? So that means I'm shifting until here. Oh, sorry, I'm shifting until here, right? That's really shifting to the right by 1 position. But if I want to shift for 1, 2, 3, and 4, I'm basically returning back to the same list, and then 5. So it will be the equivalent. So far, so good? So how exactly do we reduce any arbitrarily large number that's actually larger than the size of the list so that we can focus on some number that's guaranteed to be less than or equal to the size of the list? How do we do that? Is there any operator we can use in Java? Or should we do some complicated calculation for this? Yeah, that's good. We need a modular operator, right? And when you study the lecture for the circular array this week, for week number 7, you will see that we also use the modular operator quite intensively, right? That's a modular operator. We didn't quite use that a lot in the first year when we first learned about Java. I think as you design more algorithms, you will find that modular operator is actually very useful whenever you want to implement the idea about wrapping around. Most likely you will need a modular operator, right? Right, so given any arbitrarily large number that's larger than or equal to 0, you want to make sure you reduce that to be something that's within the range between 0 and the size. In that case, you will be able to do it quite easily, right? Alrighty, let's now go back there. So that's why n over here may not be used directly. It might be too large. I need to reduce it. So I would say number of shifts is equal to n modulo the size over here. So this will be about the number of shifts over here. That's really the number I'm going to use. And also I need this about the shift starts at, and we're going to use that little formula we derived. Size equals, size minus NOS, which we calculated over here, and then minus 1. All right, so far so good? Okay. And there's one more special case I would like to talk about over here, which is if n is equal to 0 or the number of shifts is actually equals 0, right? So this is to say, if n is equal to 0, that means we simply don't really want to do any shift, right? Or so these two are kind of different, especially for NOS. NOS equals to 0 means n is a multiple of size. For example, right? Let's see here. So here we got size 4. What if n is actually equal to 8? In that case, 8 modulo 4 is going to be 0, right? And what if n is actually equal to 120? Let's say 120. If 120 modulo 4, it will also give you 0. In which case, you just need to you just don't need to do any shift because it will be as if you did a 0 shift, right? So these two, excuse me. So these two are simply just the like a special case you want to deal with, right? In that case, I think you might just be able to say NOS equals 0 without mentioning this, because when n is equal to 0, modulo the size will be 0 anyway. So you might just be able to remove this. I kept it there just for myself to just be explicit. If n is directly 0, I just don't need to do anything. Okay. And then we're going to say return just the original head over here without doing anything. All right. Otherwise, there's at least one shift for you to do. So here, this is the case where there is at least one shift to do. I can share some experience with you right away. Okay, I can tell you that the scenario that we spoke about over here, visually over here, this one here only covers what I'm going to put down in the else part, basically. Of course, this formula as well. That's basically what I did when I first programmed this solution here. However, once I've done this one here, and when I start writing the starter test cases, I realized that if I only got this part of the code, it's not going to be enough to cover all the edge cases. So that's why I added in additional test cases and added in additional if conditionals. So this will be a similar process you have to follow for your design later. Whenever you want to implement your algorithm, I would say always think about the normal cases. And edge cases will actually follow later by some additional if conditionals, maybe additional block of code. I think that might be the way to go. You just don't need to expect yourself to really write 100% complete and correct code right away. But of course, you definitely need JUnit test cases to help you. All right. All right. For the else part, let's now do it. Right. With this particular picture in your mind. All right. Let's now do it. Let's now. Okay. So it's going to be the current is equal to head over here. Basically, this part over here, we know that the shifts will actually start at this particular value. So that's why we want to traverse to that particular node, right? So what we want to do is travel to the position where the shift starts. Pretty much like over here, right? So once I know the position to start the shift is this one over here, I need to make sure I go to that particular position, right? That'll be worst case linear time, pretty much like a get node add, of course. All right, so what should we do? We should say for integer I 0i less than shift starts at I plus plus. And I have a little exercise for you to think about, right? You can think about it and reach out to me if you got any trouble understanding it. Oh, sorry, comments. What if this part over here, rather than this, I less than or equal to shift starts at, right? Think about it. What's going to happen visually and also programmatically? Right here, I'm going to say current is assigned to current.getNext over here, right? So when I exit from the loop, I can be sure current is really pointing to this particular index, right? Exiting from the loop means current is pointing to the node at shift starts at position. All right. Remember, this is integer over here. All right. So what should we do now? So now we should really try to, for example, so let's say we're now current is really pointing to this particular node where the shift will get started. Right. What we should do is we should really set this one to be null, and then we want to actually set this one to be the head, and also set the next of this one here to be the beginning over here. Right. So these are the several things we got to do, right? But of course, the order will actually matter. Let's now just go back. Sorry, wrong way. Let's now go back to do it. Okay. So node E, we need some temporary variable to make sure once we set the let me just show you once more. Okay, because once you set this this node over here, the next one to be the null. If you do that, that means you will lose the pointer to this particular node. So that means you need to have a new head over here temporarily, right? You will need that. Okay. These are programming details you have to be you got to watch out for, right? And then we can say new head would be current dot get next over here. And then we're going to do, I can trace maybe this part of the code together with you, right? Just to make sure it's clear. And then we can say current dot set next over here. That will be just now. You can see it's corresponding to exactly what I visualized together with you. And then the tail dot set next to be the head. And of course, to return, we're going to say we return the new head. That's what we should do. All right, let me just make sure everything was okay. This one here should actually go inside over here. There we go. Right. Overall, let me recap very quickly. Either there is simply nothing for us to shift. In that case, we return null. And also, in this case, the number of positions to be shifted is simply 0. In that case, nothing for us to do. We'll just return the original list. Otherwise, we're going to do the general case where we're going to do the shift and then return the new head, right? And if I go back to the starter tests over here, let's see. Right, everything passed. All right. Right, you can compare your solution. Maybe later, if that's what you took for the test, you can compare that, or you can just do it as a new exercise for yourself. And let me know if you got any doubts, right? The final, before I do some tracing very quickly, do you guys got any question about the solution so far? Any parts you have doubts? Any part? Anybody? Is it clear to everyone? I hope. Alrighty. So let's say, let's now try to trace the code very quickly. All right. So what I will do is I'm just going to do very high level tracing. Specifically, I'm just going to focus on just this part over here, right? This part over here. Other edge cases, you can definitely do that as an exercise to trace them, right? For other test cases. And for this one here, let me just set it up quickly. So you can think about this part here is really the head. And we have I love linked lists. Okay, of course they should be string. All right, of course I think this part is also necessary to calculate the size, right? Calculate the position. All right, so this is what we can trace. And of course, initially the last node over here is simply just null. All right, let's now trace it quickly. So this line over here, we're going to get NOS is going to be n. N is going to be the argument over here. We want to shift by 2. 2 modulo, and we'll calculate the size for the list. 1, 2, 3, 4. 2 modulo 4. And we know that it's going to be equal to 2. Right? So we know that NOS is actually equal to 2. Let me use colon. The value is actually 2. And then what about this value over here? Shift will start at size minus NOS minus 1. So size minus NOS minus 1, which is going to give you just 1. What does that mean? If you look at the indices, it's going to be index 0, 1, 2, and 3. So we know that this is where the shift should really get started, right? So conceptually, what you can do is you can simply put maybe like this, right? I'll just put like that. That means starting from this point, we should really break the chain and then wrap it around, right? So this is the what really means. Over here, 1, all right? 1 over here. And then let's now try to execute this block of code over here, right? Over here. The current is actually guaranteed from the earlier loop. The current over here is actually going to be starting from this particular head over here. Eventually, after executing the loop, right, as I wrote in the comments, it's going to point to exactly where this position is pointing to. You can think about this position here is shift starts at. Right, so this is the index. And we can simply just update the current in the loop. So that's the part I'll leave to you, right? Just it's really that many of get next you have to really do. So this will be the ultimate answer over here. Let me put here. So this will be the current. Right? Current is actually going to point to that particular position. Right? So these three lines are really the ones I want to trace together with you. Okay? We need a new head, which is going to point to current.getNext. Current.getNext is really pointing to this node over here, right? That's after the basically that's where the ship will start from, and this will be the new head eventually. So what we'll do is we're going to create a new pointer over here. So that one is the new head. Right? So let's say line number 1. So this is 1. And what about 2? Current.setNext to be null. So current is actually over here that set next to be null. That means we get rid of this pointer over here. It's going to point to just null. So this will be number 2. Right? What about number 3? Number 3, we're going to say tell.setNext. So the tell, actually, if you just remember what we did earlier, the tell actually was declared over here. And after this particular loop, when we were calculating the size, it's guaranteed tell is actually going to point to the last node, right? That's something you should really notice as well. Of course, you can use a separate loop to calculate the tell if you prefer. All right. So here we say tell.setNext to be the head. So what that will do is, so tell over here that set next to be the head, the current head over here. That means we're going to set like that. Right? The whole thing is actually not circular, right? You can see this is a new head, right? So what should the new list look like? Starting with a new head over here, starting with this, which is pointing to this particular node over here. So this is the beginning of the list. And then if you follow that, it's going to be the next, which is this. And then the next, which is going to be this. And then the next, which is going to be this. And this part over here is pointing to null, right? That's basically the list after the shift by 2 positions, which will be linked list I love. So that's exactly matching the test case. All right, I hope this tracing helps about the critical part, right? Exactly how you set the pointers. Okay. Any questions about this exercise over here? So if this was the version you took, I think yep. So given 65 minutes, of course, let's say 60 because you definitely need to take some time to submit. I would say that's reasonable, right? More than reasonable to really make this right. All right, guys. Any questions?
Oh, sir, I have a question, not about this, but a general question.
Sure.
So, sir, I wanted to know like your thought process for creating edge cases. This is something I really like to know because
sure,
it's really important, I think, right?
Absolutely.
I'm sure you'd agree.
Yeah, Adnan, it's a very good question. Yes. Yeah, let me tell you this. It's a good question. Let's say in general, let's say implementing an algorithm. Okay, implementing algorithm. So number 1, visualize the normal cases. Not the you don't really think about the edge cases right away. Pretty much like what we did in the beginning over here. Visualize first of all, so you have a very good idea about how to start writing code. Okay, and number 2, implements the normal cases first. Number 3, write test cases in JUnits. I'll show you what I meant in just a moment. Write test cases to make sure step number 2, which is about implementation, is correct. I think so far so good. Your question was mainly about how to go beyond this to make sure you can cover test cases. I would say for number 4 over here, you should really try to leave, you should really shift your focus from the code into the test cases. Okay, I will explain what I meant. Shift the focus from your code, which already implemented the normal cases, right? You don't want to do that. You don't want to remain your focus there anymore, at least temporarily. From code to JUnit tests. Let me show you. Okay. As you can see, the only case, if we only program this part over here without other edge cases, at least it is going to pass test number 2. That's basically the initial test I wrote myself. Just make sure I can pass. At least I can shift by 2 positions and see exactly if that will work as expected. But what about other edge cases which will eventually come over here and also maybe over here, right? So I would say at that point, you want to go back to your JUnit test cases over here. Tests over here, right? Now you want to maybe think more about how the input list can really change its shape, input values. Because you know that over here, if you look at the how the method is being called, you need to pass maybe the beginning of some chain over here, and also some number. So these are 2 dimensions you can actually try to vary, right? So for example, in the case of the N1 over here, it could be simply a chain that points to nothing, or it can be a chain pointing to maybe 1 node, or it can be a chain pointing to 2 nodes, right? You can see the number of nodes over here will be about how the first dimension can be changed. So that means you really want to create different test cases where maybe you got a chain of 1 node, 2 nodes, 3 nodes, 4 nodes, and etc. So that's the first dimension. You always want to look back to what input values are being demanded for the method. That suggests how many dimensions you have to talk about, you have to think about. So that's about 1. And this one here is also very important because you can see from the input assumptions, we simply said the input n just larger than or equal to 0, meaning that it can be 0, it cannot be -1, of course. That will violate the assumption. It can be 0, can be 1, can be 2, and most importantly, it can be more than the actual size of the list, right? So here we got 2 dimensions so far. You wouldn't just be able to make such observation just by looking at the Java code you have implemented. You really have to go back to the JUnit test, see how the test is being used, the method is being used. Let me go back here for this particular example over here. So for example, you can see we got shifted to the right by, so here we got N1, and also we got some number N over here, 2 dimensions. For N1 over here, what are the possible scenarios? N1 could be a chain of 1 node. It can be a chain of 2 nodes. It can be a chain of 3 nodes, and etc. Meaning that you should really derive some test cases. Maybe it has only 1 node, has only 3 nodes, has only 2 nodes. You should try maybe some larger number as well, maybe up to 10. That might be just enough. Okay. The second dimension over here is about the n itself. The only constraint we have is larger than or equal to 0, right? That means it can be 1, it can be 2, can be 3, all the way to maybe the size of the list. And then it could be maybe the size plus 1. It can be the size plus 2, all the way to maybe 2 times the size, and etc. Right? You want to think about exactly how this number can be increased and then how they can be categorized. So now you have to go further to think about, since I know how this input value can vary and also how this input value can vary, how do they interact with each other? You want to think about the different combinations. For example, when the node has only size 1, in that case, the input value over here can be 0, can be 1, and can be 2, which is already double the size, can be 3 as well. So I think for the case of 1 node, it will be enough to just consider 0, 1, 2, 3. That'll be enough. And you should also consider in the case where we got 2 nodes in the chain. In that case, you can consider maybe 0, 1, and 2. So now we are reaching the size of the list. And then you want to think about 3, 4, 5, and then 6. In that case, you got 2 times the size, and etc. And then, are you so far okay? Just following?
Yes, sir. It's very
Yeah,
helpful
so I
so
think I'm
far.
just trying to give you some detailed rationale about how I derive the test cases. The point is, once you have finished programming the normal cases over here, you want to go back to examine the inputs for your particular method and think about in isolation how each input value can really vary. And then after that, you want to think about exactly how the combination of them can actually work to really give you different test cases. So that'll be my advice about how to
Sure.
proceed.
That's certainly some very helpful advice.
No problem. I think what I said over here, you can try to generalize it. I think it can be applied to many scenarios. I think that will definitely help. Yeah. Good. All right. Any other questions? Anyone? Alrighty. So I'm going to make the recording available. I'm going to make my source code available as well. So study this example, and even if that's what you did for your test, I think maybe that gave you some new insights about how to solve the problem. I think it's really important to make sure if you're given something new, maybe something you haven't seen before. In that case, how can you actually try to follow this kind of process, right? To eventually really have an algorithm that's implemented to cover all the cases. That's definitely a process you want to develop, hopefully before you graduate, right? Before you have to really dive into the workplace for real. All right, I'll wait for one more moment's final call for any other questions. Okay, and just don't forget, you still got your lectures pile up, for your upcoming weeks. I will still try to release them on time every week, so just make sure you keep up. All right, we still got 5 more weeks to go for the course. Alrighty. If you guys have no more questions, there's really no need to keep you guys longer. So I would say I will call it a day. And then tomorrow I got my final office hour for this week, 2 p.m. If you want to speak to me. And then, yep, just reach out to me if you got any other questions. All right. All right, you guys take care. I'll see you later. Have a good night. Yes.